myself Patil Yuvraj. I am working as an assistant professor in Department of Chemistry, Art Science Commerce College, Noida. Today I am delivering my lecture on photochemistry. In photochemistry, we have to see the introduction of means what is photochemistry, the basic principles involved in the photochemistry reactions, photosynthesis, process of photosynthesis reactions, and the difference between the photochemical and thermochemical reactions, laws of photochemistry, basic principles of photochemistry. Now we have to see the what is photochemistry. Photochemistry is nothing but the branch of chemistry which deals with the study of photochemical reactions. These reactions in happens in ultraviolet or visible regions. What is the actual process happens when a light of source absorbed by molecules? The molecules undergoes energy absorption and in the region of ultraviolet and visible, and the molecule goes to the excited states. After the excitation of this molecule, the molecules have some energy. When the molecules come to its ground state, the some form of energy or some form of energy will be released, and that's really in nothing but the photochemistry. For example, the best example of the photochemistry is the photosynthesis of glucose in the plants by means of sunlight. What happens during the photosynthesis? We know the 6CO2 6H2O combines to give glucose plus 6 oxygen molecules. This can you carry out this reaction and at a room temperature without photosynthesis or by thermal reactions? This reaction does not happen because the main component of this is the chlorophyll pigment. This chlorophyll pigment helps the plants to undergo this photosynthesis. What the actual process of photosynthesis happens means the water molecules absorbed by the plant roots, and that absorbed water molecules carry up to the leaves. The leaves takes CO2 from the air. CO2 from the air. The leaves during this process, the leaves trap the energy from sunlight. The sunlight in this reaction, almost most of the plant reactions are carried out in the presence of sunlight. The plants uses energy of sunlight to turn water and CO2 into sugars and oxygen molecules. The plant releases oxygen molecule into the air, and the sugar, that is the glucose, is used in the growth of plant. This is the best example of photochemical reaction, that is the photosynthesis of this reaction is nothing but the photosynthesis reaction. All we know the process of in generally photosynthesis is nothing but the cellular respiration chemical energy, that is ATP plus energy. In general, the chemical reaction accompanied with the light are by the action of light. Generally, A gives B, that is molecule A is converted into B molecule. The A new molecule is generated by a chemical changes. that is light induced reactions. But in some reaction, during chemical reaction, light is emitted. This light emitted is nothing but the chemoluminescence. The best example of the chemoluminescence is the white phosphorus glows, ignites in air to form phosphorus pentoxide, and this phosphorus pentoxide are in green in color. You have to generally uh, see this chemical reaction in atmosphere. All these are the related to the photochemical reaction. Most of you are the know the thermochemical reaction. How they differ from the photochemical reaction? The photochemical reaction involves absorption of radiation, while the thermochemical reaction involves absorption and evolution of a heat in the form of byproduct or in the form of heat. While the photochemical reaction may be carried out in the presence of light, the light must be required for photochemical reaction. While the thermochemical reactions are take place in dark as well as in light condition. The third point will differ the photochemical reaction. The temperature has a very light effect on rate of photochemical reaction. The temperature has a significant effect on the rate of thermochemical reactions. During this process, there is some energy changes or occur. That is, the energy must be Gibbs free energy. The Gibbs free energy for this spontaneous process of a photochemical reaction must be positive or negative. While for the thermochemical reaction, the Gibbs free energy must be always negative. The fifth point will differ. Photochemical reaction is a highly selective because the molecules absorb the photons and the particular group of molecule are undergoes the excitation, while the thermochemical reactions are not selective. Luminescence, we have to see the similar example, that is chemoluminescence. Phosphorus pentoxide glows ignites in the air to form phosphorus pentoxide. Similarly, we also know the light. The must needed to carry out the photochemical reaction is the light. The light is nothing but the electromagnetic field vibration spreading in a quantum. This quanta is nothing but the photon of a light. Simply we know the photon is nothing but the smallest amount of a energy, light energy carrying energy. We know the energy of a photon, that is E is equal to h nu. That it is also h c over lambda h nu. So one particle of a chemical substance can absorb only one photon from a light beam, that is E is equal to h nu. We all know the what is there. Depending on this light absorption, there is very energy levels for the firstly light energies. The light energy lies between the 200 nanometer and 400 nanometer is nothing but the ultraviolet region, while the energy between the 400 nanometer to 800 nanometer is the visible region, and after the 800 nanometer there is a infrared region. So UV and visible region, that is ultraviolet and visible region, is expected to induce a chemical reaction. Based on these, some scientists derive the laws of photochemistry. The scientist Grothers and Dropper says that only light that is absorbed can produce a photochemical change. Similarly, the other scientist says that a molecule absorbs a single quantum of light, becoming excited. This is explained by the Stark-Einstein scientist. Based on these photochemistry laws and assumptions, some basic principles of photochemistry. Photochemistry have the following fundamentals. First one is a photochemical energy. Second one is electronic excitation. Third one in excited states and modes of dissipation of energy. Fourth one energy transfer, and fifth one quantum efficiency. We can see it one by one. The first one is a photochemical energy. For any chemical transformation of an activation, energy must be supplied to molecule. Such energy can be provided by a different way. We know the photochemical energy must require a light source. The light is nothing but the E is equal to h nu. For this, some molecules undergo spontaneous transformation. In some cases, energy is supplied by increasing temperature, that is thermal condition. As a result, molecules present in the system have some amount of energy throughout the chemical transformation. In another method, the molecule present in the system involve absorption of electromagnetic radiation in the visible or ultraviolet region. Photochemical condition. Such absorption of light excites an individual molecule from ground state to an excited electronic state without affecting the surrounding molecule. Such excitations are selective. The chemistry of excited molecule differs from the chemistry of those ground state. One can change the course of reaction by activating the reactants by lighter than the other by the heat. Similarly, infrared is produced vibrational and rotational changes in the excited molecules. While the light in the visible and ultraviolet has a sufficient energy to cover the range of chemical bond energy and is able to induce chemical changes by exciting molecules to higher electronic states. Suppose we have to see the electronic excitation. We know the promotion of an electron from the bonding orbital to the corresponding antibonding orbitals. For that takes place. For that, sigma to sigma star, pi to pi stars, and n to pi stars are the electronic transitions. We have to see the molecular orbital diagram of butadiene. In a butadiene, there are a pi to pi transition occurs from psi 2 to psi 3 energy levels. That is from psi 2, that is bonding orbital, to the psi 3, that is anti-bonding orbital. These excited molecules undergoes excitation in the singlet and triplet state, and that excitation must be in the excited states, that is excited singlet state and excited triplet state. Generally, in an organic molecule, even number of electrons are paired in a ground state. Now when absorption of light of the correct energy occur, then one of the electron excited from the ground state, we see the ground state energy level is 0, that is pi, and the excited state is a pi star. By retaining the spin, so the electron pair remains paired in the excited state. This is called excited singlet state S1. In some cases, spin inversion occurs. This givings this means the unpaired electron. This excited state is called as triplet state. A triplet state is more stable than the singlet state because in a triplet state electrons are unpaired, lesser inter-electronic repulsion takes place, while in a singlet state electrons are paired causing inter-electronic repulsion and it is unstable. Based on these all things, scientist Jablonski discovered a Jablonski diagram. For that, we have to understand what is the Jablonski diagram. The Jablonski diagram is nothing but the when a molecule absorbs energy at its ground state level, that is S0 state level. When it absorbs the energy, it undergoes excitation, means the electron are shifted towards its higher energy level, that is molecule from S0 to S1, S2, S3. It may be goes to the SU level. Consider SU level. When it comes to the its ground state, there is a changes occurs. First one is a RD, that is radiationless decay. Radiationless decay means there is nothing radiation released during this process, that is molecules are generally comes its ground state. Similarly, molecules when undergoes IC, that is internal conversion, that is from SU level to S2, S2 to S1, and from S1 to S0. This happens in the same energy levels, that is SU, S2, S1. From this excited state, the molecules comes to its S0 levels. During that process, the molecules show phenomena, that is fluorescence. The fluorescence occurs in 10 raised to minus 9 to 10 raised to minus 10 second. While in similar condition, there is another process is occur, inter-system crossing. Inter-system crossing is nothing but the inter the molecule from S1 to T1 level, means inter-system crossing occurs. From this triplet excited molecule come to its ground level, that is H0, the phosphorescence phenomena occur. From T1 to S0, the process phenomena is called phosphorescence. Similarly, we have to see dates in a detail, that is what is intersystem crossing. The molecules comes from its higher S level energy to T1 energy levels. Then what is fluorescence? Emission of a photon from a singlet excited state to a singlet ground state or between two energy level with the same spin is called fluorescence. That is molecules from S1 to S0, similar energy levels, that is fluorescence. The fluorescence decays rapidly after the excitation source is removed. When the energy source is removed, the decay of the fluorescence stop. The lifetime of the electron is 10 raised to minus 5 to 10 raised to minus 8 second. While the flow phosphorescence is nothing but the emission between triplet excited state to the singlet ground singlet ground state, that is T1 to S0. The phosphorus may continue from the same time after removing of the excitation source. The lifetime is in the range from 10 raised to minus 4 to 10 raised to 4 second. Based on this, the energy transfers and photosensitization occurs in some cases. It is a one-step radiation transfer of a excitation energy from an electronic excited molecule, that is donor molecule. In some cases, a self molecule does not occur excitation. There is some sensitizers needed. This sensitizer, that is maybe donor or ground state, another molecule acceptor. Maybe one is the donor and other will be the acceptor. As a result, the donor molecule retain to the ground state and the acceptor molecule gets excited. The molecules which donate remains in the ground state and molecule will actually goes to the excited. For this energy transfer, the donor molecule should have at least 5 kilocalorie mole per energy than the acceptor. We see the typical mechanism for a triplet energy T1 transfer described as follows. The D is nothing but the donor, A is nothing but the acceptor, and 1 is a singlet state, 3 is a triplet state. When molecule D, that is a donor molecule, is at H0, that is your ground state, when it absorbs H nu, that is energy, it undergoes excitation, that is the molecules will be shifted at the 1 is nothing but the singlet, that is 1D, that is singlet excited state. When the singlet excited state molecule shifts to the triplet excited state, when the triplet excited state molecule comes to its ground state molecule, that is triplet state and ground state, and after that the triplet state molecule gives the product. The same process is occur in the 4 hexene 2 1, the energy transfer in a cis trans isomerism. Cis trans isomerization of 4 hexene 2 1 shows intramolecular energy transfer when light is absorbed by the carbonyl group. During this photo reaction, energy transfer from the carbonyl group to the carbon-carbon double bond takes place. That is, N to pi star transitions are occur. This trans isomer is converted into cis isomer. And the fifth one is nothing but the quantum efficiency. The quantum efficiency is nothing but it is the number of moles of a reactant disappearing, or the number of moles of a product produced per Einstein of a monochromatic light absorbed.